I'm Greg Scott. I'm the director of our storage software products here at Intel. And Kapil, he'll introduce himself in a second. We're going to walk you through this cloud storage solution, cloud storage acceleration layer. Talk to you a little bit about what we did with Ali, the problem we solved, and then walk you through in more detail. Kapil's going to walk you through kind of piece by piece how we actually did that from an architecture perspective. So to kind of jump in here, starting with, so what problem did we solve? So we set out to talk with Ali about how do we help them scale storage performance for their big data systems. They'd run into a situation as we were kind of moving to the next generation CPU technology, moving to PCI Express Gen 4. They were starting to see bottlenecks show up. They were being limited to the densities they were able to scale essentially by their storage. And this kind of came from both the use of hard disk drives and IO controllers. And so a way to kind of look at this is when you're using these big data workloads, so think like Hadoop and Spark, you need a lot of bandwidth. These are usually large accesses. There's a lot of temporary data going on, and you're looking at fairly large data sets, and you want to be able to scale this. And so in particular, Ollie's case, they wanted to be able to scale and utilize the full capability of these Xeon systems. And you end up with this ratio of kind of these 2 terabyte virtual disk volumes to CPU cores. And as the core count goes up, you need to just add more disks. This worked really well for a period of time up until you kind of hit this limit of there's only so many disks you can kind of shove into the system. And when you wanted to increase the density, you ran into another problem. Hard disk drives work at about 250 megabytes per second on a good day per disk. So whether that's a 1 terabyte disk, a 2 terabyte disk, or a 20 terabyte disk, you get 250 megabytes out of that disk. And so if you wanted to get deeper, higher density, you didn't get more performance. So the question was, how do you get more performance? And so that's what we started to work with Ali on. And the design goal here was faster times to insight, right? How do you analyze more data in less time? And to do that, we needed to remove bottlenecks and increase the density. So the goal was to get to like an 8-to-1, or basically looking to get like a 3x cost savings, by rack consolidation. And enter in, hey, use NAND. When you need more storage performance over hard disk drives, plug in a NAND SSD, you get great performance. And to help save on the cost side and really up the density, QLC seemed like a great solution. But when we did that, we found that you actually run into some problems. So in this environment, when you're trying to scale both the capacity and the performance, it doesn't scale as nicely and as linearly as you'd like. And there also, with QLC in particular, there's some endurance challenges. So this is what we set off to work with Ali to go solve. And we actually spent almost a year working with Ali, going through a number of different scenarios, working through some different tests. And it kind of boils down to, there's 11 tests we really kind of focused in on. Some of them were application kind of simulation workloads. Some of them were just sort of corner cases to see and stress the architecture. Ali did a really great presentation at the SPDK Summit last year in December. They kind of walked through a lot more of the detail of this and some of the other scenarios we looked at. But what I wanted to highlight here was 2 factors with this software that we've focused on. One is we were able to achieve an 8x improvement in overall system performance benefits. So that think the big data workload itself sees an 8x improvement in performance when we implemented this software. And we were able to bring in Optane to kind of help balance out the QLC technology. And then the other one that's interesting, and it really kind of goes to why we were able to see that performance and if we can sustain that performance, is on the random 4K write. So we were using these large capacity, high indirection count SSDs. So they were inexpensive from $1 per gigabyte perspective, very dense, not a lot of over provisioning. But the challenge with that is random write performance, especially 4K random write performance, was really poor. And we were able to essentially up that by about 35 times. So that really goes to how our software is able to help sequentialize and manage the way we're placing data onto these NAND devices. And this allows us to really extract the full value of NAND and be able to scale both from a performance and a density perspective. So what did that kind of look like? We went from just being an SSD to we added in an Optane SSD and sort of did an Optane QLC pair. And that now allowed us to scale modularly. So you could offer it up as smaller devices. So like 8 2 terabyte devices, 4 4 terabyte devices. And so, but as you did that, you got to scale both the number of those devices. You could use the full capacity, but you also got to scale the performance. So you offered 4 terabyte devices, you got 500 megabytes per second, if you will. And so this gave a lot more flexibility to Ali. And we see this, as a very valuable feature from talking to other customers. This is one of the things we're very interested in as we go forward and you look at kind of where the NAND technologies are going with QLC, PLC, ZNS devices. And Kapil will talk a little bit more about how that fits into the architecture in the future. So this is a technology that we're just starting to introduce. It's an open source, cloud scale, share nothing software architecture. And it's part of SPDK, so we're working on getting it into the SPDK community. It's really focused on helping to unlock and scale the use of NAND, both from a performance and capacity perspective, so we can bring the performance to the rest of the system and scale the performance of storage along with the scaling and the density increase in CPU and core count. We're leveraging Optane as this ultra-fast caching device and write shaping function. This is what allows us to improve system performance as well as manage the way we're writing and placing data on QLC, so we're not burning it out, we're not slowing it down, and you're really getting to maximize the performance out of that device. It takes advantage of the PCI Express Gen 4 directly off the CPU, so we don't introduce any bottlenecks by going through bridges or I/O controllers, so it really gives you that full performance access and really unlocks the multi-tenant QoS that is necessary to be able to really scale that density and really take advantage of these deep drives. So you can kind of break them up, give them to different VMs, give them to different tenants, and still extract value without having one tenant interfere with another. And you can kind of see here, this is the instance that Ali is offering based on this technology. It's available today, it's an invite testing, and you can see how they're able to break it up and allow multiple tenants to sit on the same system, and you can offer different sizes, if you will, based on what the customer's needing. And this is really a key part of enabling both Ali as a service provider, but also customers of Ali to take advantage and really buy what they need and get what's the performance necessary.
Thank you, Greg. My name is Kapil Karkra. I'm a software architect on CSAL, and I will be walking you through the architecture of CSAL. So architecturally, CSAL implements a flash translation layer, much like NAND SSD vendors implement inside SSD. The main difference is that CSAL up-levels the FTL to the server level. In fact, you can think of the storage node shown as a big black box around this slide as a giant 1 petabyte SSD that offers 1,000 1 terabyte high performance virtual disks. And they are served to multiple cloud tenants. And I'll be filling in this black box more as I walk through the architecture. But let me hit 3 main points as an overall top level points here. So inside the box, the first thing to note is the bottom layer, which is a much larger pool of high density cost optimized NAND. That's your 1 petabyte NAND flash. And then what else is inside this box that I'm showing right now? It's the top layer. And the middle light green box is the CSAL software. CSAL software is written, like Greg mentioned, from ground up for simplicity and scalability. It's lockless, shared nothing architecture that scales linearly in performance as we add more cores, memory, etc. resources. And what else do you see in the top layer? Of course, Optane. There is, for 1 petabyte, you would need about 50 terabytes of Optane SSD capacity which is about 5% of 1 petabyte in this box. So CSAL uses Optane at the global level for storing both L2P, logical to physical mapping table, which is shown on the right-hand side, and write buffering caching, which is shown on the left-hand side. So you can think of our software, CSAL and Optane, the entire top layer, as the layer for managing any vendor's high-density NAND bottom layer. Without this top layer, high-density NAND has fundamental challenges with performance and endurance that you cannot overcome. That's as Greg pointed out in his section. So maybe I can pause here for a moment, take any questions before I jump into layering in and filling in this box with 6 architectural components.
Is CSAL an architectural thing, or is it an Ali specific thing, or is it an industry thing?
So you will see in the next slide, it will show we are upstreaming it as an open source cloud storage acceleration layer. It'll be open sourced. We implemented it with Alibaba, but we are open sourcing it, and it's a very general purpose. Like I said, you can have Optane and our software front any NAND, high density cost optimized NAND, and it works. It's a very general purpose software.
Thank you.
Okay, so let me then one by one layer in the architectural components. So the first component is the flash translation layer. This flash translation layer exposes the compatible 4K granularity random block interface, so no changes to the existing applications. The higher density NAND interface, you may have heard the term zoned namespaces. That's the emerging high density cost optimized NAND interface. It's called ZNS. That ZNS interface requires applications to change, and ZNS interface has constraints like you have to write a minimum size of 64K, IO size of 64K, and data must be written sequentially. So without honoring those constraints, QLC NAND performs worse than HDDs. So the FTL component here that I'm showing meets these constraints by landing writes on Optane write buffer, merging small writes into large ones, and those writes are aligned, and then writing to NAND sequentially. So this results in 35x improvement versus raw QLC that Greg showed earlier. The FTL also implements garbage collection, crash recovery, and some of the specific DevOps cloud-related features like live software upgrade in less than half a second. The next component I want to talk about is the logical to physical mapping table. This is the map of applications view of logical block addresses to how we map them to the physical blocks on the media. So for a 1 terabyte capacity, we would need a 1 terabyte of DRAM to hold this dictionary lookup mapping table. That's a lot of DRAM. That will be too expensive. So what we do instead is we take tiering approach. We put hot parts of the logical to physical mapping table on DRAM, and then we page in and page out to a small partition on Optane SSD. Now, this tiering scheme does increase our crash recovery complexity. So in our target implementation, aligned to with CSAL 2.0, we will move to persistent memory. And then we won't need the complex paging logic, checkpointing, etc. And we would also gain the performance benefits we would get from CSAL. The third component is the persistent write buffer and cache. So all writes, like Greg mentioned and I mentioned earlier, land on Optane SSD in this architecture. As application writes come, they land on Optane. This is where the 8x improvement on the big data workloads come from. So it is because of Optane caching. So big data workloads generate a lot of temporary data that is frequently written and read. This temp data gets absorbed in Optane and gets read out of Optane, which results in both saving QLC life, because that data will never need to be destaged to QLC. So it increases QLC life. as well as it improves the overall performance because you're reading and writing to Optane mostly. In future, persistent memory offers even lower latency than Optane SSDs. So when NAND migrates to, let's say, PCI Express Gen 5 and Gen 6, we plan to use CSAL 2.0 and CSAL 3.0 attached persistent memory, and also Xeon integrated data streaming accelerator, which is one of the accelerators available starting Sapphire Rapids Xeon scalable processors to achieve this much higher performance write buffering caching for this architecture.
A quick question there. You said you were planning on connecting which product or technology with CSAL 2.0?
So for what we are going to change is today our persistent write buffer and cache is Optane SSDs. And what we are going to do in future is we're going to migrate this write buffer cache to persistent memory. And the data mover, we won't use CPU as a data mover. Xeon CPU will be running software, data services, etc. software. The data movements will all be done by our data streaming accelerator, which is an integrated accelerator on the Xeons.
Okay, thank you.
Does that make sense?
Yes.
All right. So then the fourth component here is the storage analytics piece, which helps us achieve the performance consistency, quality of service, and further mitigate some of the write amplification that we see and noisy neighbor effects in among multiple tenants in cloud environments. So right now it is mainly separating the writes from our internal garbage collection and writes from different tenants, but in future we'll add additional capabilities. And the fifth component that I already built here at the bottom is the cost optimized NAND tier. So this is where currently we are using 5316 QLC drives from old Intel, now it's Solidigm, those drives for the Ali deployment, for Alibaba deployment. We will be migrating over time to ZNS, zone namespace drives. That's where we will unlock full cost optimizations of high density NAND. Those ZNS SSDs won't need any over provisioning, so they will need zero OP over provisioning, no XOR logic, no power fail protection logic on the SSDs, and even more RAM reductions because individual SSDs don't need to hold their mapping table or their write buffer. So we simplify the NAND, high cost optimized high density NAND, the ZNS NAND tremendously, and we do the work at the global level to reap the economies of the scale. And the final piece, the sixth component here is the RAID piece. So we integrate RAID function at the global level because, like I mentioned, ZNS SSDs that are cost optimized will drop XOR, and therefore they will also drop the reliability, Uber, etc., by 2 to 3 orders of magnitude. So a local RAID implementation at the box level that we're doing in CSAL, it makes sense. There is another reason that the RAID implementation makes sense. So in cloud, you might have heard we use distributed erasure coding and replication. But as the SSDs get larger, think these cost optimized NAND SSDs to be 64 terabyte. Rebuilding these SSDs once an SSD fails will require a lot of network bandwidth. So local RAID starts to make sense where we can quickly rebuild within the CSAL and heal the SSD or recover from the SSD failure. And by the way, our RAID implementation is a full stripe RAID because we can keep things in persistent write buffer longer. We don't incur, a traditional RAID incurs RAID write hole and bunch of other penalties that we won't incur. Our RAID 5 and RAID 6 will perform like RAID 0, actually. So 2 to 3x better endurance and performance versus traditional RAID. So in summary, CSAL architecture preserves block interface, so applications don't need to change. It uses Optane as cache to deliver high performance for workloads like big data, Spark type workload, Hadoop Spark type workloads. And for write shaping, we also use Optane as a write shaping to make sure we make the writes to NAND very NAND friendly, large, aligned, sequential writes. And most importantly, CSAL and Optane enable high density NAND in cloud, really. We need this top layer that I talked about. CSAL together with Optane is the key enabler that actually enables that low cost NAND.
So Kapil, is there a reason that you've chosen RAID 5 and 6 rather than more dynamic erasure coding?
So RAID is, because it is fixed, it is much more CPU efficient, meaning the number of instructions it takes to execute an erasure code is much higher versus implementing a RAID 5 and RAID 6. And we have done the reliability calculations. It makes sense to basically, the RAID 5 and RAID 6 are sufficient, basically. We don't need that flexibility within a box, because this RAID is within a box. It's not like a distributed RAID. It makes sense to do RAID 5 and RAID 6.
Okay, yeah, I figured it was going to be a trade-off thing. I just wondered whether it was, but wanted to understand what that trade-off was. And this is just within your system, because I think you mentioned you're assuming that there will be other forms of resilience on top of this. This is just
exactly right.
To protect the data within this system, which is just the acceleration layer anyway.
Correct.
Okay.
So with the RAID 5 and 6, are you actually doing a read, modify, write if there's new data, or are you just doing a new write and invalidating the previous 64K block?
We are doing the latter. Basically, it's a full stripe write, meaning our cache tier in Optane will always hold the full stripes and then destage those full stripes, and the previous locations will be invalidated, like you pointed.
Okay. But so what? What workloads would this technology best benefit? Would it be purely machine learning and analytics? Would it be data warehousing, data lakehouse? Would it be online transaction processing, OLAP, ROLAP? Or is it just all of the above?
Let me actually answer that question for you, Kapil. So the whole point of this is that you have the ability to build out very large portions of storage, and you can divvy it up among various different workloads and supply each one of those workloads certain capacity and certain QoS associated with it. I know this because this is basically the solid layer architecture from 10 years ago.
Oh, okay. Well, thank you.
I may add very quickly that for Alibaba, this is the big data Spark Hadoop deployment. They're deploying it first there, but the gentleman who spoke is right. This is general purpose. Okay. So this is the last slide. Greg, do you want to quickly cover this?
Sure. Just kind of wrapping up here. And I think there were a couple of questions around this. So CSAL is meant to be open, available, general purpose. We're, to help facilitate that, we're upstreaming it into SPDK. We're working on that right now. So it's actually visible and available if you're interested. It's going to be delivered as essentially BDEV modules in SPDK. So it's modular, it plugs in. We're going through the review process right now. We're going to continue to be adding new features. So technologies like RAID, support for ZNS, support for PLC going forward. Those will be implemented upstream in the SPDK community. And we're also looking at building this out because one of the other places we see this becoming very exciting is the emergence of this NVMe over Fabrics solution. So this as Kapil kind of walked through that architecture, think of this as a 1U 1 petabyte essentially super drive that you can then divvy up thousands of virtual volumes to and share at sort of the data center scale. And that's, we're going to start with a reference architecture kind of showing that off. And our goal is to have an initial version of that by the second half of this year. And then there's some references here if you're interested. You can go actually play with the software right now on Alibaba. You can check out some more of the details behind the architecture and some of the trade-offs and some of the different things we looked at, traditional caching versus what we're doing with this kind of right shaping technologies, we call it. And then some additional system level benchmarks will be coming soon as we're, working with Ali and, exploring how to show this in actual working systems and the benefits that you get in actual real life solutions.
I have a question from Twitter and this would be for Christy. Will third generation PMEM use second or third generation Optane?
It's using second generation Optane media.
Yeah, one on the CSAL architecture, because there was talk about that being an open standard, I think. Is there software available, or like an online repo where people can go and kick the tires on it a bit?
Yes, it's available on SPDK right now. If you go to the spdk.io, you can get to their repo and it's available as a patch.
Yeah, it is available as a patch. SPDK core maintainers are reviewing it, and our plan is to upstream in SPDK repo by May. So the May release of SPDK, they do regular releases, and May release, if everything goes as per plan, will have the CSAL inside the SPDK.
I'm going to ask a question which is maybe the elephant in the room, but a lot of people are, talking about that online as the presentation was going on. Intel Optane predates the CSAL standard, so it's really great to see that you are somehow converging your technology with a standard which was released afterwards. But a lot of people are thinking about compatibility, right? And they're wondering if Optane, the next generation of Optane, the CSAL enabled Optane, is going to be compatible only with Intel Xeon processors, or if it's going to support other x86 processors, not to make any names.
So let's put it this way, the CXL standard is still in development. So I would say we have very limited visibility into what types of devices and functionality are being built into all of the various processors and controllers out there. Our approach right now, just like it has been with starting with a minimum viable product in the first generation and moving forward, is that we're doing all of the design, the validation, the optimization around Xeon. And we're not actively going out and trying to connect to other types of processors. But it is going to be a CXL compliant device. And so depending on how everybody implements these things, there could be compatibility. Just we're not designing for it or guaranteeing it at this point in time.
Yeah, thank you. That really helps a lot. I think that what you've been doing with Optane has been really kind of transforming the way. It's even been helping build some use cases that we've seen with Meta that were not possible before. So, my personal opinion as a closing comment from me is that having this kind of open approach will really be even more boosting the adoption of storage class memory for other use cases, which we may not even see at the point. Thank you.
Yes, thanks for the comments.